Okay, thank you very much. As mentioned, my name is Michael Nasello. I'm a machine learning engineer at StratumAI, and I'm going to talk about some of the work that I did at a Simberi mine. Okay, so what were we trying to accomplish? We wanted to use qualitative and quantitative data to predict throughput at the mill, essentially how much material can we push through per hour. So this case study, this is a project that I got to work on. It was a lot of fun. I'll give you a little bit of background on the deposit. It was a epithermal gold deposit. They gave us about 250 kilometers of drill hole data and about 510 kilometers of grade control. And so what kind of value were we trying to create? We wanted to create a mapping function that maps the attributes of each block to the expected throughput of that block. The goal is to forecast plant throughput for plant blocks on a daily basis. Our main goals for accomplishing this, we want to identify the pathfinders that contribute to throughput of a block, and then we want to model throughput of the block directly using those pathfinders and compare against baseline functions currently used by the mine. Before I get into that throughput project, I'll do a little bit of background on strata models and how they work. There's 3 steps. The first step is we take the existing mine data that they have, so drill holes that are used to create the kriging models, lithology data, metallurgy tests. Second step is we put all of that data into one of our AI models. We have a bunch of algorithms that we've designed, and what they essentially do is learn the geological patterns of your data set from this historical data. And third, we generate a full block model of whatever parameter you are trying to predict. Typically with our customers, it'll be gold, silver, copper, but we do many more. In this case, specifically for this project, the parameter we're trying to predict is throughput. I'll talk a little bit about the data flow of our AI models. So it doesn't really matter if it's a drill hole or a blast hole. We can handle lots of different things. But in this case, on this slide, we're talking about drill hole and blast hole data. What we'll do is we'll separate them into a train and a test set. Either we'll split them spatially or temporally. We'll take the data from the training set, we'll feed it through our neural network, compare our predictions to the true data that we see in the mine, and then we do this learning process via error correction. Once we're happy with how the model has been trained, we will evaluate it on this test data that the model has never seen before to make sure that the metrics that we are creating are up to par with the standards of our customer. Okay, it's a bit hard to, in such a quick time, explain the architecture of how these AI models work. I'm going to do my very best to do so in such a quick time. But if you are genuinely more curious, I sincerely encourage you to come visit our booth, and I can have a very in-depth conversation about how these things work because they're very cool. But this is generally one of our CNN architectures. So on the very left, where that picture of a mountain would be, your data set would go in there, and we apply a series of kernel filters. These kernel filters are responsible for learning these geological patterns that power this model. There are only like 4 or 5 on this picture, but generally we're talking about hundreds or thousands of these filters that are absorbing very complex, deep relationships within your data set. The output of these filters is passed to a multi-layer perceptron, and that condenses all of these outputs of these filters into eventually one number, which would be the parameter you're trying to predict, whether it be gold, copper, silver, or throughput. Okay, back to throughput. So on this graph, the blue line you're looking at, that is the daily throughput readings that this Simberi mine was experiencing. The red is their prediction for how much throughput they think they're going to experience based off of the input, the material input. As you can see, the red line is not doing a great job of tracking the blue line, so they came to us. We have a relationship with them. We have models, AI models actively deployed with them, so we wanted to collaborate and see if we could do something better. Okay, so we trained a model to predict the sag power required to crush the material going into the mill. When we trained this model, we could take a look at what features were driving the predictions of our AI model. So the graph on the left is your geochemistry, the graph on the right is non-geochemistry. So you can see some common elements like iron, gold, copper, zinc, calcium. Those are ones that come up often for geochemistry. And then for non-geochemistry, we have RQD, lithology, field strength, etc. So we did a pretty decent job. So if you look at the blue line, sorry for the colors, probably not the best, you can see the sag power readings that they were experiencing as they pushed material through their mill. And then the gold dotted line would be our cross-validated predictions. Because we generate predictions on a block level, some cool things we can do is actually aggregate for each deposit and tell you on average how much sag power we think is going to be required to process a block. So I have this table up here, a couple of different deposits, and how much sag power on average would be required to process a block. This was for CIL material, and then this was for float material. Okay, are we done from there? Unfortunately, we realized we weren't, and that is essentially because of this scatter plot you see here. Although sag power and throughput required to process material is highly correlated, as you can see by that pretty straight line, there is a decent amount of variation across that line, and that caused some issues for us. So as you can see, when we take a conversion from sag power to throughput via these linear functions the mine provided to us, we had this constant issue of underprediction. So again, the blue line is the throughput, and then that gold line is our sag power predictions with a linear transformation to the throughput space. Again, underprediction, so we weren't done with the problem yet. Because of that, we decided to model throughput directly. And so I have another model, a throughput model, and similar to before, we were able to track the features or the categories that are driving how our AI model performs. You're seeing a lot of common geochemistry elements. So you have calcium, sulfur, iron, moly, silver, copper, and then on the right, there's one feature that's really dominating the results, and that's the crusher state. I'm going to get to that in a second. But you also have your lithology, your RQD, and such. Okay, so after training our model, it's doing a pretty good job. The blue line is the correct throughput that was experienced on the day, and then the green line is our predictions when we directly model for throughput instead of sag power converted. We're able to achieve on average for each day mean absolute error of 34 tons per hour. So when we condense all of these predictions by day and look at monthly averages, and we look at all of our models combined, you can see that there is clearly one winner. The blue is the true monthly average throughput. We have the red, which was their predictions, the gold, which is when we modeled for sag power and converted, and then the clear winner, which is the green, where we directly modeled for throughput. Okay, I mentioned in a couple slides about that DB crusher state. This is pretty interesting. While I was building this project and we were doing our modeling, in the middle of it, Simbiri actually added another circuit to their mill, so they're essentially changing the phenomena of the problem. And so they told us what date they switched their crusher, and then they gave us more data to add to our data set. We retrained our model, and it was pretty cool how our model could pick up on what was happening, whether it be with the new, more powerful crusher or the old one. What we did is we ran a simulation looking at all of the blocks across the ore body. What does it look like when we use the old crusher, and then what it looks like when we use the new, more powerful crusher. And the results of this simulation, you can see it doesn't matter if it's economic material, if we're looking at their dig packets or their mine plan shells. It's pretty cool to see how when we move and we simulate with their new crusher, how much better we do on throughput. There's a lot of numbers on that table. It might be easier to look at it visually. So I'll point you to the first two graphs. These are cross sections of the bench at a random area in the mine. So the middle graph, you are seeing the throughput simulation when you have the old crusher. And then you can see as you move from that image to the one on the far left with the new crusher, given the scale, we're getting an uplift in throughput. So to summarize essentially what's happened, they came to us and they were trying to predict throughput. They were having issues. The model was not tracking the true values properly. We were able to get a 70% reduction in our MAE. We found material behavior. The sulfide material showed stronger response than oxide, consistent with expected process dynamics, and some geochemistry, some elements that were very useful for predicting throughput. They had higher predictive power, or iron, calcium, moly, sulfur, etc. Okay, that's all I have for you today. If you have any questions, please approach me on the side or meet us at our booth. Thank you.